Graphical representation of simple harmonic motion. We already derived the differential equation of simple harmonic motion. From this equation, we know that second order differentiation of position, which is d square x divided by dt square, is equal to minus k by m into x. Now, if we solve this differential equation, the solution of this differential equation is xt is equal to a cos omega t plus phi. So from this we see that the position of the object or the particle in case of simple harmonic motion is a function of time, which is vary with time. So xt is equal to a cos omega t plus phi. So in this equation or in this solution, a, omega and phi are all constants. Just only t is varies with respect to time. So t is varies mainly, it is the variable, okay. So the position is dependent on time. Now if we draw a graph, position versus time graph mainly, so the graph will be just like that as shown in the figure. So when time is zero, the position of the particle is maximum because cos 0 is 1, phi is also 0, the phase is also 0, okay. So the result is xt is equal to a. So the maximum displacement is a here, okay. Then time to time, particularly the position will vary. So the graph is like a particularly cosine graph, okay, starting from the maximum amplitude, okay, maximum position mainly. Then here a represent the amplitude. This is the maximum position in either positive or negative x direction. And omega is the angular frequency, which is equal to root over k by m. We already discussed about in earlier, okay. So omega is angular frequency, this is root over k by m, spring force divided by mass, root over spring force divided by mass, and the phase constant is represented by phi, or which is called initial phase angle. Where a and phi are determined by initial conditions, okay. So in initially, if the amplitude or the displacement, initially displacement is represent the amplitude and initial phase represent the phase constant or initial phase angle. Remember the time period and frequency. So we already discussed about that. Frequency is related to time period by this equation f equal to 1 by t, and which is equal to omega by 2 pi. So from this equation we can say time period is equal to 2 pi by omega. So t equal to 2 pi by omega. And we can also say that there is a relation between angular frequency and normal frequency. So omega is equal to 2 pi f, okay. So these are the basic equations. How can we determine the time period or angular frequency or normal frequency, okay. Now motion equations for simple harmonic motion, okay. So the solution of the differential equation is xt is equal to a cos omega t plus phi, which describe the position of the object or position of the particle, and figure a describe the shown the graphical representation of this equation x equal to a cos omega t plus phi, and start from the maximum position xi, okay. And if we differentiate this position, so because we know that first order differentiation of velocity, differentiation of position gives the velocity. So the velocity of the particle vt, which is a function of time also, so vt is equal to dx by dt, which is equal to minus omega a sine omega t plus phi, because the differentiation of cos theta gives the minus sine theta, okay. So we have to differentiate omega t also, so that's why there is a omega constant omega. So the velocity in simple harmonic motion vt is equal to minus omega a sine omega t plus phi. And figure b describe the graphical representation of the velocity. This is basically velocity versus time graph, and it starts from the initial position, mainly here initially velocity is 0, Okay, and the second order differentiation of position x gives the acceleration. So here acceleration is also function of time because acceleration is not constant, velocity is also not constant in this case. So at is equal to d square x by dt square. This is the second order differentiation of x, or first order differentiation of velocity is equal to minus omega square a cos omega t plus phi. So from this we see that particularly position and acceleration has basically same graph, cos graph, but the sign is different, so that's why their phase is opposite direction. Okay, so the velocity is 90° out of phase with the displacement. Okay, because the graph is cos and sine, so the difference between cos and sine is 90°. So the velocity is 90° out of phase with the displacement, and the acceleration is 180° out of phase with the displacement, because mainly they are same graph, cos graph, but the sign is opposite. Okay, so here figure C describe the acceleration versus time graph. Okay, and from this graph we saw that there is a particular relation between graph A and graph C, a similar graph but in opposite phase only. Okay, now example of simple harmonic motion. So if we started from the maximum displacement, so initial condition when t equal to 0, the displacement is maximum, then the velocity is 0. That means initial phase angle is also 0. Then if we put this value in the equation of acceleration and velocity, then the maximum acceleration will be plus minus omega square a at plus minus a. So when displacement is maximum a, then acceleration is omega square a, and when displacement is in the negative direction and maximum minus a, that gives the maximum acceleration is minus omega square a. And the velocity, the maximum velocity is plus minus omega a at x equal to 0. Okay, so that's just only different direction. Okay, so the position is same in equilibrium position, but due to different direction, velocity is different. Okay, so one is plus omega a, another is minus omega a. And here these three graphs shows the position versus time graph, velocity versus time graph, and acceleration versus time graph. Okay, now the second example of simple harmonic motion. So here the difference is in initial time t equal to 0 second, consider the displacement is 0. So if the displacement is 0, then the velocity is mainly there is a particular velocity at 0 second, t equal to 0 second, which is vi, and that means there is a phase difference phi is equal to minus pi by 2, which is minus 90°. The graph is shifted 1/4 cycle to the right compared to the graph of x is equal to a. So mainly just 1/4 cycle shifted from the previous one. Okay, so here figure B shows the graphical representation of x versus t, velocity versus time, and acceleration versus time. So here we saw that particularly the graphs are mainly shifted 1/4 cycle. Okay, now let's talk about the energy of simple harmonic oscillation, because we applied a force and this force produced some motion. So this motion is related with the energy. So the spring force is a conservative force. So in a frictionless system, the energy is constant. Okay, so there is no friction involved, and the force is conservative force. In case of conservative force, energy is remain constant. The kinetic energy, which is related with the velocity, is k equal to half m omega m b square, mainly k equal to half m b square, which is equal to half m omega square a square sine square omega t plus phi, because we know that velocity is equal to omega a, mainly minus omega a sine omega t plus phi. So if we calculate the omega b square, which is equal to omega square a square sine square omega t plus phi, then the kinetic energy is equal to half m omega square a square sine square omega t plus phi. From this equation we can see that the maximum value of the kinetic energy is depends on the sine square omega t plus phi. So if the sine square omega t plus phi is maximum, then kinetic energy is also maximum. The maximum value of the sine omega t plus phi is 1. So if you put the value of the sine omega t plus phi is 1, then the maximum kinetic energy is half m omega square a square. Okay, and the potential energy of the spring, which basically if we just extend the spring or just particular compress the spring, the energy stored in this spring is potential energy, okay, which is elastic potential energy mainly. So its elastic potential energy U is equal to half k x square, which is related with the displacement and spring constant. Okay, so potential energy in case of spring U equal to half k x square, and we know that displacement x is equal to a cos omega t plus phi. So if you put the value of x in this equation, potential energy is equal to half k a square cos square omega t plus phi. And from this equation, we can see that maximum potential energy is also depend on the cos omega t plus phi. The maximum value of the cos omega t plus phi is 1. Then potential energy, maximum potential energy is half k a square. Okay. Then the total energy or total mechanical energy is the sum of the kinetic energy and potential energy. So total energy E equal to k plus u, which is equal to half m omega square a square sine square omega t plus phi plus half k a square cos square omega t plus phi. And we know that omega is equal to root over k by m. Then if we put the value of omega equal to root over k by m, then the kinetic energy is also equal to half k a square sine square omega t plus phi. So the total energy is half k a square sine square omega t plus phi plus half k a square cos square omega t plus phi. So if we take the common, they take half k a square common, then half k x square first bracket sine square theta plus cos square theta. So sine square theta plus cos square theta is 1. Then finally the total energy is half k a square, which is constant, and total energy is proportional to the square of the amplitude of the oscillation. Now the transformation of energy of simple harmonic motion. So you know that total energy is conserved in simple harmonic motion. So the two energies involved, kinetic energy and potential energy. So if we say that particularly there is a decrease and increase in energy, basically kinetic energy or potential energy, and it converts into another form, mainly kinetic energy convert into potential energy and potential energy convert into kinetic energy, but the total energy will be remain same. The total energy is constant at all times and is E equal to half k a square. Energy is continuously being transferred between potential energy stored in the spring and the kinetic energy of the block. So in this two plot, in figure A and figure B, which is basically a kinetic energy, potential energy versus time graph. Okay, in both case, okay, in second case, basically kinetic energy, potential energy versus amplitude graph or position graph. So in both plot, kinetic energy is constant, and which is equal to half k a square. Okay, so from this we can say that the energy is remain constant in case of simple harmonic motion.